Good morning, students. Continuation of the previous topic, system of particles and rotational motion. In that, relation between the torque, moment of inertia, and angular acceleration. Torque tau, moment of inertia I, angular acceleration is alpha c. The relation is tau equal I alpha. For theory examination, actually derivation is not there, only formula you need to remember. And this formula is very important for the problems purposes. For object in rotatory motion, velocity is always along the tangent. If the force is applied along the tangent, on external force place, when force is applied along the tangent, then velocity will change. The angle between the velocity and the radius is always 9 degrees for circular motion. And the torque is equals to Rf sin theta. The force changes the velocity, and so acceleration is produced. F equal to ma from Newton's second law. A is taken as at, called the tangential acceleration, acts along the tangent of the circle. At that instant only we are considering as instantaneous tangential acceleration is at. It is due to the change in velocity magnitude, but not because of direction. Due to change in direction, what you get is centripetal acceleration, that is toward the center. But here we are talking is change in magnitude of velocity, which produces a tangential acceleration at. In the examination, they don't mention a subscript t, they simply mention as a. That is not centripetal acceleration. Careful with that. It is a tangential acceleration. At is a tangential acceleration along the tangent to circular path. M is the mass of the particle. It's not a big object. We are taking it as a particle for simple cases. R is the radius of circular path or circle. Alpha is the angular acceleration. The relation between the angular acceleration and tangential acceleration is A equal to alpha. We have already discussed before. And torque tau is equals to Rf sin theta from the definition. R sin theta is called as the perpendicular distance, but theta is 9 degrees. Sin 90 is equals to 1. So this sin 90 is 1. What you get is tau equal to Rf. But F equal to ma. F equal to ma at or just a. And a equal to alpha substitution you do, you will get tau equal to mr square into alpha. But mr square is nothing but equal to moment of inertia I, so torque equal to tau equal to I alpha. This is applicable not only for particle, even for the solid object, continuous distribution of the mass, any object, tau equal to I alpha is applicable. Even for the system of particles also it is applicable. That the system of particles is taken the resultant conditions. Total moment of inertia, total torque, total angular accelerations. Next is another relation is relation between the angular momentum L, moment of inertia I, and angular velocity omega. L equal to angular momentum, I is the moment of inertia, sometimes we represent symbol m dot I, and omega, it is not W please, omega is equals to angular velocity, R is radius of the circular path, m is the mass of the particles. Consider particle of mass m moving in the circular path, velocity is along the tangent to the circle always, perpendicular to the radius. The relation between V and omega is nothing but equal to V equal to omega R. And angular momentum from definition is moment of momentum. Linear momentum is angular momentum. It is also equal to the linear momentum into perpendicular distance. Perpendicular distance is nothing but equal to r sin theta. Perpendicular distance at the momentum, mass into velocity is moment, the direction of the momentum is along the tangent only. Momentum and perpendicular distance from the axis of rotation is, that means perpendicular to the radius. That means theta is 90 here, sin 90 is 1. R sin theta is perpendicular distance to the momentum. L is equals to mv into r sin theta, this part is 1, therefore what you get is mv r only. But V is equals to omega, substitute m into omega into r is m into r square into omega will get. What is mr square is nothing but equal to moment of inertia. I equal to mr square for the particles. Therefore, you will get the relation as L equal to I omega. It is applicable not only for the particle, even for the solid bodies also the relation is applicable. So these two formulas you need to remember. One is tau equal to I alpha and L is equals to I omega. Next point is law of conservation of angular momentum. Law of conservation of angular momentum. Already you have conservation of linear momentum. Conservation means what? A constant. But there is a condition for that. What is the condition is, for the linear momentum P equal to mass into velocity. If velocity and mass both are constant, momentum is constant. Both in magnitude direction unit constant because momentum and velocity are vectors. And force, external force is nothing but equal to, from Newton's second law, dp by dt or delta p by delta t. Rate of change of angle, linear momentum is nothing but equal to external force. And if there is no external force, means external force equal to 0. Then in that case dp by dt equal to 0 means p is supposed to be constant. Means mass into velocity is constant. That is called as a conservation of linear momentum. You will be learning in collisions with the example of collisions. During collision, before and after collisions, momentum is conserved because whatever the force acting between them is supposed to be internal force but not a external force. But if external force is applied, then if external force is not 0, then momentum is not constant, it changes. Before momentum, after momentum, not constant. In the case of the elastic and inelastic, both the cases what we consider is external force is 0 if you have taken, then momentum is conserved we have taken. Total momentum before collision equal to total momentum after collision. So this, once again I have to repeat this. P is equals to mass into velocity and external force is equals to dp by dt equal to 0, then P is equals to constant. This one you have to apply for the conservation of angular momentum. In the case of this is for linear motion, straight line motions. For rotational motion, what we take is this is replaced with the angular momentum. Momentum replaced with angular momentum. Mass replaced with the moment of inertia. V replaced with the omega. And force replaced with the torque. If there is no external torque, then angular momentum is constant. It is called as a law of conservation of angular momentum. Definition. If there is no external torque, then angular momentum of the system is constant. If there is no external torque, then angular momentum of the system of particles, or you can take object, whatever you consider, is constant. What is the formula for external torque and angular momentum relationship is external torque tau ext equal to dl by dt or delta L by delta t. What is dl by dt is called as a rate of change of angular momentum. L is angular momentum and dl by dt is called as a rate of change of angular momentum. In case if you are taking the rigid body, then L is equals to I omega we can consider. I is moment of inertia and omega is angular velocity. Omega is angular velocity. So if there is no external torque, then dl by dt equal to 0, so L is equals to constant, that means L equal to I omega is constant. If there is no external torque, if there is any internal torque, so they do not affect the angular momentum, only external torque we need to consider. If there is external torque, so tau external equal to dl by dt equal to 0, therefore L equal to I omega is equals to constant. It is constant. In case if I changes, what happens, then moment of inertia by any reason changes, omega changes. So I is L equal to constant means therefore I is inversely proportional to omega. Or we can say omega is inversely proportional to I. If I increases, omega decreases and vice versa. Or also we can also say that or I1 omega 1 is equals to I2 omega 2. If I increases, omega decreases and vice versa. If I increase, then angular velocity omega decrease. Vice versa means if I decrease, then omega increase. Moment of inertia decrease means omega increase. I will explain the examples. how it changes. Condition is that there is no external torque. Applications. Of law of conservation of angular momentum. Application of law of conservation of angular momentum. Person rotating on swivel chair, or you can take or on turntable or on turntable. In your textbook example, they have given it as a swivel chair, means rotating chair. The person is sitting on the chair. Okay, I am going to discuss on the turntable. Procedure is similar only. Turntable means one frictionless rotating disc is there. On this rotating disc, it is pivoted on the sharp point. Person is standing on it. With the hands stretched. It may be in just as hand stretch you can take, or you can take some weights in the hands, that will be more effective, you will find. And rotating with angular velocity omega 1. And by stretching the hands, moment of inertia of the body increases. I equal to mr square. So therefore r is more from the r is the distance of the total mass from the axis of rotation. If the r increases, means moment of inertia increases. I equal to mr square, or proportional to mr square. Proportional constant is different for the different shape of the objects. Depending on the axis of rotation changes, but I equal to proportional to mr square. R is the distance of the mass from the axis of rotation, and this r increases means moment of inertia also increases, resistance also increases. So first case, let us take this mass are kept it far away from the hand body, axis of rotation, and omega 1 is angular velocity, I1 is the moment of inertia. So angular momentum becomes equal to L1 is equal L equal to I1 omega 1. What if the person folds the hands? This is rotated initially with this angular velocity omega 1. Disc is rotated. Actually, angular velocity acts along the axis of rotation, but we generally diagram it represents along the direction of rotation, but it is not true. It acts along the axis of rotation. Next, the person folds the hands. When he folds the hands, the mass is moved close to the axis of rotation. Then mass r decreases. Whenever the r decreases, moment of inertia also decreases. The moment of inertia here it is I2, angular velocity is omega 2. There is no external torque acting on it. You are not applied force from the outside. The person only just stretching the hands and folding the hands. What happens if you stretch the hands? The moment of inertia increases. If I increases, omega decreases. If when you fold the hands, I decreases, therefore omega increases. Here, initial values is L1. L is equals to L1 equal to I1 omega 1. Hands stretched with the stretched hands, and final values L2 is equals to I2 omega 2. Folded hands, folded hands, these are final values. But there is no external torque, therefore L1 is equals to L2. Tau external equal to 0, therefore L is equals to constant, means or L1 equal to L2, that means I1 omega 1 equal to I2 omega 2. Here which is less, I2 is less than I1. Here I2 is less than I1. Hence, when I is decreased, omega increases. Hence, omega 2 is greater than omega 1. Automatically, speed increases. Again, if you fold, by folding, speed increases. By stretching the hands, speed decreases. Same thing happens instead of standing on this rotating table. If the person is sitting on the rotating chair, effect is similar. Other examples. the person diving or in the circus jumping from one swing to other swing. A person in the circus will hang to the swings and jump to the other swing. Jump to other swing. While jumping, he folds his body. By folding the body, what happens? Initially, he has to take some angular velocity and just to twist and then jumps. While after jumping to other swing, he folds his body so that moment of inertia decreases. When he folds the body, the moment of inertia decreases. Whenever the moment of inertia decreases, I decreases means omega increases. So speed of rotation increases. He rotates, he makes some loops. Whenever you want to stop the rotation, he stretches the body. Whenever the stretch of the body is done, I increases, omega decreases. And when he reaches the other swing, then he stretches the body so that he can catch the swing easily and stands vertically. So a person, if you want to rotate more, he has to hold the bodies and stretch the body. The rotation decreases. So second example, diagram is not actually required. Person jumping from one swing to other in circus. Perform acrobats. It's called as acrobats, it's also called as somersaults. Somersault or acrobats means rotating the body in the air. Perform acrobats by folding the body. When you want to stop the rotation, he stretches the body. To stop the rotation, he stretches the body. Whatever will stretch the body, moment of inertia increase. Therefore, I increase and decrease. So I can say, therefore, he changes moment of inertia I to change the angular velocity of rotation. Same thing if the person is diving into the swimming pools. If the person is diving from the diving board into the swimming pool, he has to take compulsorily some initial theta. The theta change is nothing but equal to omega. Omega is nothing but equal to d theta by dt or theta by t. Rate of change of angular displacement theta is itself is omega. Omega is there means rotation is there. Theta is also related to rotation. So initially must take the theta and takes a jump from the board. When he taking the jump, he is already having some angular velocity. Without having angular velocity, the person is jumping straight up. Omega is 0, theta is 0. In that case, omega cannot be changed. What is required is compulsory some initial omega is there means you can increase or decrease. Initial omega is 0 means you cannot increase or decrease. So here he must not straight jump. If he jumps straight, he falls there only. He has to make some angle and then rotate, jump up. While jumping automatically has taken some omega, and after jumping he folds his body and rotates. When he wants to stop the rotation, he stretches the body. When he stretches the body, then moment of inertia increase, I decrease. While rotating, he actually while taking the jump, he will take the parabolic path. Which part of the person is taking the parabolic path means the center of mass. Center of mass has only linear motion. Person may rotate, but the center of mass has a linear motion which takes the parabolic path. Okay, and center of mass may lie outside the person also while rotating. It may be little outside also, not inside, but it is the boundary of the persons. So this person jumping in the swimming pool performs acrobats or somersaults by taking the help of law of conservation of angular momentum. Person jumping or diving, better said, diving into swimming pool. Perform the acrobats by taking the help of law of conservation of angular momentum. Next is ballet dancers. Ballet dancers, they rotate on the tip of the thumb of the leg and they stretch the hands and one leg and rotate, spin on the tip. The angular velocity is omega 1, moment of inertia is I1. By stretching the hand and leg, okay, this spins. And whenever they want to change the speed of rotation, what they do is they fold the hand and legs. If they fold the hand and legs, by folding the hand and legs, what happens is I2, moment of inertia decreases to I2, and angular velocity omega 2 becomes greater than omega 1. So speed changes. This is a ballet dances. Moment of inertia increased if you stretch the body, hands and leg, one leg, and if you fold the hands, the moment of inertia decreases, omega increases, because L is equals to constant I1 omega 1 is equals to I2 omega 2. If I increases, omega decreases, and vice versa. Similarly, in case of animals like cats, monkeys, the animals which have the big tails, not elephant, okay, and even dogs also try to use the tail while taking the jump from one height to other height, or jumping, leaping, or jumping from monkeys jumping from one tree to other tree. They take the help of this tail to control the moment of, to change the moment of inertia and to control the speed of rotation. Especially if you take the cat is known that it will never fall on its back. If you are dropping the cat, never try to do it, because cats may bite you. And cats, if you take in reverse, back down, if you take the cat in reverse, and if you drop it, it takes a jerk from your hand from angular velocity, then it rotates. It rotates its body by folding its tail. It folds the tail and also body, even the body and the legs and head. It does very fast, automatically it is. And whenever the tail is bent, to that moment of inertia decreases. Whole body folding means moment of inertia decreases. The result is angular velocity omega increases. Initially it takes some omega for taking the jerk from your hands. So this omega 1, moment of inertia is I1. So omega increases and moment of inertia decreases. And whenever the legs comes downwards, then it stretches the tail and body. Whenever the tail is stretched, automatically rotation decreases. Whenever the moment of inertia increase to I2, omega increase means much than I1, so greater than I2. Is already I2, I will take this I3 is greater than I2, and omega 3 is less than omega 2, previous one, compared to the rotational motion I am taking. So moment of inertia increases means omega decreases, and it can land on the feet, onto the ground. So these animals take the help of their tail to increase or decrease the moment of inertia, thereby controlling their angular velocity of rotation while taking a leap or jump from one height to other height. These are some applications of law of conservation of angular momentum. While walking on the thin wall, automatically we stretch our hands. What we are doing there by stretching the hands is we are increase the moment of inertia, so that stability automatically comes. And the people rope walkers, people who are walking on the rope, they take the very big pole in the hands and they stretch it horizontally to balance it. That is to increase the moment of inertia. Bigger pole you take, better stability you will get. This cycle wheel. If you are making it stand on the wheel without rotation, it is not possible. It will fall either left side or right side, but it can be made to stand while the cycle is in motion. What is happening there is because of moment of inertia. We already discussed that point before. Due to the moment of inertia, more stability while rotating on it. So when cycle wheel is rotating, cycle is moving, it is able to stand on the wheels only without falling to the sides. Even if you push the person also, it won't fall because of the property called as the moment of inertia. To increase the moment of inertia, the thin spokes are used so that the mass is located at the end points. More mass at the end, more R value for the masses, more is the moment of inertia. This is like a circular ring. You can take moment of inertia equal to mr square. But if I take this stand like this, it will be horizontal. It cannot make it stand like this. It will fall to the sideways. But in case if I make it rotate, in case if I make it rotate, spin, then it is able to stand on this axle rod. It is able to stand vertically because of moment of inertia. But here conservation of angular momentum also takes place. It is trying to rotate with the same angular velocity, but due to the friction the speed decreases. Whenever the omega decreases, what happens is, to conserve the angular momentum, it will provide one more rotation about this vertical axis. This is called as precision. The top also rotates in the same way. This is one angular velocity momentum torque acting along this axle rods. If the rotation is like this is the direction of the angular momentum L, and a friction force is providing the torque that is trying to reduce the angular momentum. Whenever the speed is reduced, L is equals to I omega. Omega decreases. Whenever the omega decreases, it is trying to maintain the L constant, so for that it provide one more angular velocity that is about this vertical axis. Depending on the direction of rotation, it may rotate clockwise or anti-clockwise about the vertical line passing through this axle rods. That is called as a precision. The rotation is called as a precision. Whenever the speed decreases, automatically it will not come to stable and it will fall to the sideways. The speed decreases, it cannot stand like that. It is going to become horizontal. While rotating only, it is stable in this position. That is due to moment of inertia, and it is trying to conserve the angular momentum. This conservation, this moment of inertia is a property which makes it stable also. That principle is used in this device called as a flywheel. This flywheel and gyroscope. The gyroscope toy is also there. Flywheel, in any machinery parts you will find very heavy wheel. Even the cars and the bikes, motorcycles, in all these missions, even in the, if you see the sugarcane juice point, you will find aside one heavy wheel. Even in the small toys, the key toys also, inside you will find one heavy disc toy. That is nothing but called as a flywheel. Free rotating wheel with a large moment of inertia is called as a flywheel. For this flywheel, moment of inertia should be large enough, so that once rotated, it keeps on trying to rotate due to the property called as a moment of inertia. L is equals to I omega. If I is large, L is also large. So it's trying to keep the L constant because of the property called as a moment of inertia. And here, that vehicles, cars, bikes, etc., continuous fuel but is not burned, so you will get the jerks of motion will be there. To reduce the jerks, we take the help of flywheel. So flywheel is used in the automobiles to reduce jerks, jerky motion, jerks of motion. To have the smooth motion, we take the help of the flywheels. And the same thing is also called a gyroscope. Gyroscope is also heavy disc rotated and with the help of the motor and fixed inside the aeroplanes, inside the ships and inside the rocket and satellites also. As it rotates, it tries to rotate in the same direction with the same axis of rotation. So due to that reason, to provide the stability for the devices. If I rotate in the particular direction, try to remain in that same stationary only because of the property called as a moment of inertia. So gyroscope provides the stability for the aeroplanes. If the wind comes, not heavy ones, wind comes, it will not be disturbed. Ship also will not be disturbed. Rocket also in the particular directions. Satellite can be rotated in the particular position only with the help of this gyroscope.